Okay, welcome back. So in this video we're going to actually start to simulate the physics of our game because it's all based on this kind of bouncing ball mechanic. So it's going to be really important to get that right. We're going to look at concepts from physics like position, velocity, and acceleration. That's going to help us implement that behavior. And then we're also going to use concepts from the JavaScript language, things we learned like variables and functions. We're going to learn how to translate the definitions of variables and functions that we know from math into the language of code. And then what's going to help us do that is using the basic math operators like addition, subtraction, multiplication, division. And then finally, all these things are going to be dependent on time, so we're going to look at part of the P5JS library that will help us keep track of how much time has elapsed. So in this game, we're going to have to simulate gravity. And what gravity actually is pretty complicated. And we know a lot about it thanks to Albert Einstein, but we don't really have to understand it in his terms. He understood it as the sort of warping of the fabric of space-time. And we don't have to understand it quite to Einstein's level in order to make this game, because all we really require is this kind of 17th century understanding of gravity. So we're going to go back to Isaac Newton. And he understood, just as we all understand from our everyday experience, that if we drop an object, it's going to be accelerated toward the center of the Earth. And he quantified this acceleration due to gravity. He determined that it's going to be pulled toward the Earth at negative 9.81 meters per second squared. So we'll find out more about what that means as we go along, why it has these strange units and everything. So we'll start with an overview of some of the math that we're going to be working with. So our end goal is going to be to obtain an expression for the position of an object. So we're going to call that x of t, and we need some math that describes that. So to break it down, we need a few variables. We need to know what's the position. We also need to know the velocity. So velocity is like a speed, but it has a direction as well. We need acceleration, and we're going to call that a. And of course we need to keep track of time, so we'll call that t. So first, we know what position is really, but we're going to formalize it and talk about what exactly we mean by position. So if we take an object in the real world, we need 3 coordinates to describe what its position is, because we have 3 degrees of freedom. Of course we can move up and down, we can move left and right, we can move forward and backward. So there is a coordinate for each of these degrees of freedom. And we could label the axes, we'll call them x, y, and z. And if we have a value for each one of those, then we've completely described the object's position in 3D space. So in our game, we're going to be taking that down to 2 dimensions. So we only need an x and a y coordinate. But before we even do that, we're going to take it down to a simpler one-dimensional case, and it's going to make this all this math easier to understand. So if we restrict ourselves to talking about objects that can only move left and right, we're talking about one-dimensional motion. So we'll just use x to represent the object's position here. So our first crack at describing how the position of an object changes over time is going to be an object that's not moving. So all we need to describe this object's position over time as time changes, we need an initial position, and we're going to call that x sub 0 or x naught. So if we want to make this example a little bit more interesting, let's say we have a car, and we know that the car is moving at a velocity of 30 meters per second. And we'll say that the object is at position 0 when we start the experiment. So if we let this car drive at its constant velocity for 2 seconds, then it's pretty easy to intuit what the answer is going to be here. What the final position is going to be at the end of 2 seconds, because all the information we need is contained in that velocity term. It's the definition of velocity, how much distance is covered over time. So if it covers 30 meters in a second and it runs for 2 seconds, then we have 60 meters at the end. And we could get that by multiplying the amount of time that's elapsed by the velocity term. And it's always good to keep track of the units. So if we have 30 meters per second, we have a second in the denominator, and then we multiply that by time, and time is measured in seconds. So that in the numerator in the time term, that seconds cancels with the seconds in the denominator, the velocity term, and we have meters left over. So even the units work out, so that's great. We could define the final position as the velocity times the amount of time elapsed. And if we want to add an initial position to that, remember we started at 0 in this example. If we wanted to add a non-zero initial position, that's just going to add to the velocity times the time elapsed. So this is our first proper functional notation for the position over time. So if now we want to extend this to 2 dimensions, we already have most of the information we need. We've gone through the process, so we just have to extend it a little bit. So say in 2 dimensions, the velocity of the object might be entirely vertical, it might be entirely horizontal, or it could be a combination of horizontal and vertical. So for any velocity that's, say, diagonal in some direction, we can do what's called, we could decompose it into its horizontal and vertical components. So imagine drawing a horizontal line and then kind of projecting that, that diagonal line down onto it. So here we have the horizontal component of the velocity. So here we have the equation that we had before in the one-dimensional case. We just have an initial x-coordinate, and then to that, of course, we add the velocity in the x direction, the component of the velocity in the x direction, multiplied by time. And we could do that with the y-coordinate as well. And that describes the vertical position of the object over time. We have an initial vertical coordinate, and we add the vertical component of the velocity multiplied by time. It's as simple as that. So you can imagine generalizing to 3 dimensions, even 4 dimensions, 5 dimensions. We can't visualize anything at that point, but this math generalizes. So you'll have one of these equations for every dimension you want to add. Okay, so now the big question is, how do we translate all the math that we know to code that can implement that math, that can take in numbers and kind of churn them and produce the result that models those equations? Well, this is where we left off last time, and I'm no longer going to randomize the diameter of the object. We're just going to have a fixed diameter, so I'm going to take out that random call. So we'll make this diameter 20 pixels. Okay, and before we start actually modeling the physics, I want to highlight something about the way I've declared this variable. So this is the only way we've seen a variable declared so far, and it's not the only way we can do it. So let's say, before we start to get into position, velocity, acceleration, let's do something with this diameter. Let's say every time we draw a frame, we want the diameter to increase by 1 pixel. So as the program runs, we want the circle to get bigger and bigger and bigger. So if we wanted to do that, then we have a problem, because every time this draw function is called by this environment, what happens is this variable is declared and given a value of 20. So that means we can't add 1 to its value if we're declaring it every time. So what we really need is a variable that exists independently of the draw function. And that way it has a value and it holds on to its value each time the draw function is called, instead of just being declared inside the draw function. So what I can do is take this, and I'm just going to cut it, and I'm going to go up here right at the top level. I'm going to insert a few lines and put diameter up there. So what this does is it gives me a variable that exists outside of all these functions. So before, when diameter was declared inside the draw function, I could only refer to that variable inside the draw function. If I tried to do something with diameter inside of setup, it wouldn't know what to do. And I could actually show you that. I'll put that back here. And I'll try to print diameter. Okay, and I get an error. Diameter is not defined. And that's because I declared this variable inside the draw function, so it only exists as long as that function runs. If I instead declare diameter up here, and I try to run, now I could print the diameter. This variable has an independent existence now. Okay, so I don't need that. I'm going to take it out. So now what we could do is do something like add 1 to the value of diameter. So if I were to do that, this is going to look a bit strange at first, but I'll explain exactly what it means. Okay, so diameter equals diameter plus 1. Now, if you saw this expression in a math class, it wouldn't really make any sense. How can the value of a variable be equal to the value of that variable plus 1? It's kind of nonsensical. But in code, when you see an expression like this, what it really means is take the value of diameter, add 1 to it, and then you get whatever this is, whatever that result is, assign that value to the value of the diameter variable. So when you see an equal sign, it's important to remember it's not equality in the mathematical sense. What it means is assignment. So the old value of diameter plus 1 becomes the new value of diameter. Okay, so now when I run this, the circle should initially be 20 pixels. Every time it draws a new frame, the circle is going to get larger by 1 pixel. All right, does what we needed to do. Good. Okay, so there is another way that you'll see this expression implemented that means exactly the same thing. So if there's a special operator. Now by operator I mean these symbols, like addition is an operator, assignment is an operator. So there's an operator that kind of condenses this a little bit because I have to type the name of the variable twice. So if I get rid of that and instead I do diameter plus equals 1. Okay, what that means is exactly what the old expression meant. So if I run this again, we should get the same exact behavior. Great. Okay, so this is going to be a useful expression, and if instead of getting larger by 1 pixel on each frame, I wanted it to get larger by 10 pixels, that means add 10 to the variable of diameter and overwrite the old value of diameter. There we go. Okay, so this is a really useful expression that we're going to use throughout this video. Okay, so for now I'm just going to get rid of that, and we're just going to keep diameter defined up here. So what we really need now is a few extra variables to represent the position of the object. So let's say let position x equal 0, let position y equals 0. And now something, we could do basic things with those position variables. Well, first we have to substitute them in. So instead of mouse x and mouse y, we're going to draw that circle at whatever the variable says its position is supposed to be. So we'll copy that, paste it there, copy position y, paste it there. Alright, so if I run, of course, that should just be up here in the upper left at the origin, and it shouldn't change. But I can do basic things like position x plus equals 10. Okay, so we're adding 10 to that position on every frame, so we should see it move across the screen. Good. Right now I want to make that change that I made in the last video. I actually want to put this background function before the call to ellipse. So that way we'll only see we'll see the circle only in one position at a time. There we go. Okay, so now you could see this 10 kind of represents the velocity in a way. unfortunately, we don't have any precise control over how the position changes over time. Now recall, with velocity, it's defined in terms of meters per second. So we have to be keeping track of time, and we need some unit of distance. Our unit is going to be pixels instead of meters. So this is moving 10 pixels on every frame, but how do we know how much time has elapsed between frames? We don't really have any information to tell us that. So I'm going to get rid of this for now. And what we are going to see is how do we keep track of time. And there's a function in the P5JS library that does this for us. It's called millis. And there it is. So when we call this function, millis, it returns how many milliseconds have elapsed since the setup function was called. So basically since our program started running. And it even tells us this information is often used for timing events and animation sequences. So it's going to be really useful for us. And it's a function that takes no arguments, so we call it like that. Okay, so if we were to use this function inside draw, then what we could do is, well, let's create a variable out here first. Let time equal 0, and then we'll say time equals millis. And then just to start out with, we'll print that variable to see what the value of it is. Print time, so we should run that. And okay, so we see the value of that variable changing. So we'll go back to the code. And if we want to model a moving object that's moving at a specific number of pixels per second, what we really need to know is, instead of what time is it, we need to know how much time has it been since the last time we drew a frame. So to do that, it's going to take a few extra variables. So what we need to do is have 3 variables total. So we'll have time 0, that's like our initial time, time 1, and then we'll create one final one called d time. And d time is going to be the difference in time between frames that we drew. Okay, so I'll get rid of this. So what we're going to do is we're going to say millis, whatever value that returns, that's going to be time 1. And then d time is going to be time 1 minus time 0. And then after we've done that, this is important that this has to happen in this order. Time 0 is going to be time 1. Okay, so let's break this down. So this means every time we draw a frame, we get the current time, and then we determine how much time has elapsed since the last frame by taking the current time minus the previous time, and then the new previous time is going to become the old current time. So that way, next time we call this draw function and it gets back up to the top, this time 0 variable is going to contain the time 1 value, variable value from the last draw function call. So here, if we print, let's do this, we'll print d time. This should give us basically how many milliseconds did it take the computer to draw a frame. So we'll open up the console again, and just pause it to see what's going on. All right, so this time between frames is varying quite a bit. It's because my computer is doing a lot of other things. It's simultaneously doing a lot of tasks. So there's going to be some variability in how long it takes to draw a frame, and that's to be expected. But as long as we know how long each frame took, then we can keep our physics accurate. So now what we could finally do is define a velocity. So I'll say let velocity in the x direction equal 10. And what are those units? I'm going to put in what's called a comment that helps us remember. I don't think I covered this yet. So if we put in 2 slashes, anything I put on this line after those 2 slashes is going to be ignored by the computer. It's not code, it's just to help us read. So it's so I could, for example, to help me understand what this code is doing, I can say velocity in the x direction is in units of pixels per second. So then we'll have a velocity in the y direction, and we'll just make it the same for now. And as long as we're putting in units here, let's put in pixels as the unit of position that we're working with. And these variables are going to be in milliseconds. I think there's 2 L's in milliseconds. That's fine. So before we continue implementing moving object using a velocity term, I want to take a quick look back at these equations that we were looking at before. So I want to just highlight now that this we're going to basically be modeling this equation as if it represents each frame of the animation. So what that means is that our initial position is going to be the initial position of the object on every frame. And then the velocity is going to be whatever the velocity is in that moment. And then t is going to be how much time has elapsed between frames. So we'll have x and y coordinates of the object. And then on every frame, we'll take the velocity in both of those directions. We'll multiply it by the amount of time that's elapsed, and then we'll add it back into those x and y coordinates. So what that's going to look like is this. It's going to be position, and to that we're going to add velocity in the x direction times, so if we're defining this as pixels per second, and this value is in milliseconds, then we have to do some scaling here. We have to convert milliseconds to seconds. And we know that there are 1,000 milliseconds in every second. So that means we'll take d time divided by 1,000. And then to implement the velocity in the y direction, we'll just take this equation, we'll copy it, and we'll paste it right down here. And then we'll just change all the x's to y's, since that's how we called our variables. And that's really all there is to it. So we should see, when we run this code now, we should see the object moving diagonally down from the origin in the upper left at a rate of 10 pixels for every second. So it's going to be pretty slow. And there's our slow moving object. So we should be able to increase, let's increase it only in the x direction. So let's increase it by a factor of 10. Okay, so it's moving down at this kind of shallow slope. And then if we increase the y component of the velocity as well, then we should see it moving diagonally down the screen again. Great. So that takes care of velocity for us. So I'm just going to clean this up a little bit, align things so they look nice. So before we move on to modeling acceleration, we're going to look back at the math before we do that. But I just want to highlight one more thing here. Our draw function is getting pretty long. And when code gets really long, you have to read it from top to bottom to understand what it's doing. And the more steps you have to read through, the harder it is to keep track of what's going on. So in programming, it's really useful to break out our code into smaller chunks, and that way it makes things easier to understand. So what we're going to do is break this up, this function up into 2 more functions. So I'll put in a few lines of code here. And the first thing we're going to do is, I don't need to print the time, so I'm going to get rid of that. I'm going to put these 3 lines of code in their own function. So I'll create a function using the syntax that we learned in the last video. We have function, then the name, we have a set of parentheses. If we want arguments, we could put them in the parentheses. We need curly brackets to open and close the body of the function, and that's going to define a block of code. So we'll have function, and now we could give it a name. So if I'm putting these 3 lines of code into a function, I want to give it a name that describes what it does. And I'm just going to call it get time. Open bracket, close bracket. Okay, when you're creating a function, I highly recommend you do it this way. So you first define a function with an empty body, with no code in it. That means create the opening bracket and the closing bracket at the same time. That way you don't forget a bracket, and you won't end up dealing with all these weird error messages that have to do with unbalanced brackets. Okay, so I'm going to take this code now and I'm going to cut it, and I will paste it in here. Now I could shorten this up. And of course the really important thing we can't forget to do is we have to call the function. So I've just defined it here. So inside the draw function I have to call get time. And since this is a simple function that doesn't take any arguments, basically this line of code just runs these 3 lines of code. So it's a way to just break it up into these manageable chunks. And I'm going to do the same exact thing for these 2 lines of code. I'm going to create a function called update position. Open curly bracket, close curly bracket. And I'll cut these 2 lines and I will paste them in here. And this code is going to run fine if the code isn't indented properly, but it just looks really messy and it gets harder to read. Trust me. As the complexity of the code increases, if things aren't indented right, it's a big mess to look at. So keep your indentation lined up. So again, like we did with the getTime function, we can't forget to call the function. So update position. I'll just clean this up, get rid of the white space, and this should behave exactly like it did before. So if we run it, then we get the same behavior and we're good. So all we've done is just reorganize the code. So now if we want to understand what the draw function does, okay, the draw function gets the time, it updates the position, it sets the background color, and it draws an ellipse. That was pretty easy to read through. If we had to instead read through all these individual lines of code, then it would have been more difficult to understand what it does. So again, with this theme of organization, it's part of writing really well organized code is using things like comments as well. So sometimes you'll see comments right next to variables where they're defined. A comment can tell what the variable is in case it's not obvious by the name, or in this case we're putting in units for the variable. We can put in comments right above our functions that describe what the function does. So this function getTime computes the time elapsed between frames. And this function update position, we could say adds the velocity term to the position terms. Let's say adds the velocity terms to the position terms. So this is for both the x and the y directions. And now we're in really good shape. This code is very clean, it's very readable, and it's very organized. Okay, so where we started was we needed an expression for how the position of an object changes over time. And we've modeled that using position, velocity, and we're keeping track of time. Now we just need to know how to model acceleration. So we're going to be adding another term to this equation, basically. we actually already understand everything we need to know about acceleration because we've already modeled position and velocity. So the analogy here is that velocity is to position as acceleration is to velocity. And if you think about that, it makes sense because velocity is the rate of change of position. So that means acceleration is the rate of change of velocity. So if we want to understand that a little bit more precisely, we have to look at the math. So these are our equations we had before. So instead of having Vx and Vy like this as fixed values that don't change over time, we're going to make Vx and Vy functions of time in their own right. So we're kind of adding another layer onto this simulation. So we'll say velocity is going to be changing over time. So we'll have some initial velocity. And to that, we're going to add a contribution due to the acceleration. And we're going to multiply the acceleration term by time. And then that's going to be the value that we add to velocity. So we're going to model this in the code. It could be modeled a few different ways, but the way that's most convenient for us, given how we've structured the code already, is to model these as another set of equations, because we already know how to model these equations. But if you want to understand the form of these equations when you see them in physics class, you'll more commonly see these velocity terms substituted back into the original equations. And when you do that, you get these polynomial equations. So you have the initial position, velocity times time, and then the acceleration times time squared. But the sets of the equations on top are the ones that we're going to be using, and they're exactly equivalent to the ones on the bottom. And just for the sake of completeness, it's always nice to make sure the units work out. So before we saw that acceleration has these units of meters per second squared. So why are the seconds squared in the denominator? You can look back at the equations that we're working with, and you'll see that they have to be. It's part of the definition of acceleration. So if we take the units for each one of these terms and we add them together and we do all the cancellations, then we see that in the acceleration terms we have the second squared canceling with the second squared that results from squaring time. And we could see that the second cancels with the seconds in the velocity term, just like it did before. And then we're left with meters plus meters plus meters. So our resulting position has the units of a position variable, in this case meters. In our simulation, we're substituting pixels for meters. And the units work out in the same exact way. So again, we're going to simulate acceleration in our game using the sets of equations on the top. We're separating how velocity updates position, and we're separating that from how acceleration updates velocity. And it's going to make our code a little bit easier to manage. Okay, so from here it's really easy actually, because this is going to look exactly like the process that we did to add velocity to our position. So to add acceleration, we're just going to create two more variables. I'll just call it Excel to keep the variable name short. In the x direction, we'll make that 0. So we're simulating gravity, so there's going to be no acceleration in the horizontal direction. But we will have acceleration in the vertical direction. So let's make it something like 500. And we won't have this constant velocity term anymore. All we really have to do is, when we create these variables, velocity x and velocity y, we'll make them 0. And then our acceleration variables will do the work of changing those velocities over time. So we'll make that 0, make that 0, line things up again, and I'm going to put in some more comments here. This is pixels per second, which is just another way of saying pixels per second squared. Again, the process is the same. So instead of putting the code in the draw function like we started before, we're just going to start with a separate function. So I could even call it before I define the function. So I know it's going to be called update velocity. So I can take that function name, copy it, and then I can put in function, and then I'll paste in that name I gave it. It's going to take no arguments. Open bracket, close bracket. And then it's going to look exactly the same as this, except instead of velocity updating the position, it's going to be acceleration updating the velocity. And then I'll just copy that line again here, copy, paste, and then change that to velocity y being updated by acceleration y. And then I'll add in a comment. So this adds the acceleration terms to the velocity terms. And I've already put in the function call, so if we run this, it should just work. We should see the ball at its initial position, which is in the origin, and we should see the ball accelerate downward. So it should look something like how an object accelerates when you drop it toward the earth. So that looked pretty good. It started out very slowly, and then as it dropped, it got faster and faster. So we'll rerun that to see it again. Great. Okay, so one last tiny thing to make it a little bit easier to see what's going on, since it's not at the edge of the screen like that. We'll change its initial position. We want to put it in the center of the screen. So if we want to do that, you might make a guess that since we have these variables window width and window height, we can just do something like position x equals window width divided by 2. If we do that and we try to run it, we get an error. So this is important. Window width is not defined, it says. So if we go back to the code, sometimes certain variables are not accessible at the top level. And that just has to do with how P5JS is doing some of this work under the hood that makes it easy for us to write our code. But what we could do is keep that at 0 right there, but in the setup function, we'll create the canvas, and then we'll say position x equals window width divided by 2. And that should run fine. By the time it gets to this setup function, it has a value for this variable window width, whereas up here at the top level, it was before it ran setup, it didn't really know anything about the window yet. It hadn't gotten that information. So we should be able to run this, and we should see the ball now in the middle of the screen dropping down. Great, beautiful. Okay, so just to summarize, we learned some physics. We learned that velocity is the rate of change of position, and we learned that acceleration is the rate of change of velocity. And since those two things were similar in their relationship to one another, we can implement them with the same exact approach in our code. We also learned a little bit more about the JavaScript language. We learned how to declare variables at the top level so that they have this sort of independent, like persistent existence, and that any function that we create can modify those variables. We learned how to use functions to break up our code into readable, manageable chunks, and we learned how to use some of the normal math operators. I don't believe I went into detail about this, but they have all the normal order of operations rules. So if you're familiar with how to use, say, a calculator, a scientific calculator, then you know that the operators are evaluated with parentheses, exponentiation, multiplying, division, addition and subtraction in that order. In programming, in almost every programming language, it maintains that same order of operations. And then finally, we learned a really useful piece of the P5JS library that we can use anytime we need to be keeping track of time, like simulating physics. We know we could use the millis function to give us the number of milliseconds that have elapsed since the program started running. And that'll be it for this video. Join us in the next one and we'll learn how to simulate collisions between objects that we can use to help our ball bounce when it reaches the bottom of the screen.